Hi, and welcome back to the channel. Today we're delving into the fascinating world, for me at least, of material science and failure modes, okay? And here we're going to explore three critical types of failures, that being ductile, brittle and fatigue. We're going to look down and break down each of the sort of failure means, how they occur, and understand what is critical when we look at engineers designing and inspectors inspecting structures that are at risk of these types of failures. So whether you're a student or a professional, somebody who wants to learn more, or just curious about how metals behave under stress, this video is for you. So let's get started. So the first failure mode we're going to talk about today is ductile failure. Now this occurs when materials undergo significant plastic deformation, normally through something like overloading. So if we put too much weight into a structure or too much stress. This is generally the type of failure we want to see, if that's fair to say, because we can design it out really easily just by making our materials strong enough or have a high enough cross-sectional area to be able to take the expected stress within our structures and our design. Okay. When we have failure, ductile failures are characterized by deformation, so necking, and elongation, so getting longer, right? Now, the necking and elongation mean that the material will never return to its original size. So we also need to look at how we keep away from this yield point at which we move from being elastic to plastic. We never really want to be in plastic. So with that, let's have a bit of a deeper look into the mechanics around this phenomenon. So one of the best places for us to start when we're looking at ductile failure is our tensile test graph. This graph can be used to understand a lot of different points and is used quite heavily within the welding inspection exams. So it's good to make sure you've got a good understanding of where you are with it and you can name all the different parts, right? But what we're going to do here is we're going to take a sample and we're going to start applying a force to it, right? Now, as I pull my force, you can see my stress and my strain increase, right? Now, the way I simplify it in my head, stress is the amount of force we're putting into something, strain is how long it's getting, okay? If you think about it like that, you'll not go far wrong, okay? Now, if I'm in this first area of my tensile graph, this is my elastic zone. So when I let go of it, and I let it return back to its size, it release the stress, it should return back to its size. Okay. This is the best place to keep all structures and where we're kind of aiming for that to be in general. Okay. Now, if I let it return back to its neutral state, and then I reapply my force again, so I pull it up to the top of its elastic level, and then I continue to add force. What's going to happen is we get to this point of the graph. And you can see these lines bouncing up and down and moving. Now this is what we refer to as my yield point. Now we tend to term yield as RE, which means resistance elastic. Okay. Now, this is the point at which if I let go of my sample, it will no longer return back to its original size, and it's met what we call its plastic or its elastic limit, and it's now in plastic deformation. Right? We never want to be here in a welded or a fabricated or welded structure, because at this point we're pretty much done, right? The material isn't doing what we expect it to do, and now it's getting longer. If you have a bridge structure, you never want to get to this stage, because it means you've kind of knacked your bridge. Okay. Now, if we look at these parts, what we'll see is we've got like a top level and a lower level, upper and lower. to the yield as it bounces around. Okay, so this is our upper yield point and our lower yield point. So the way to think about the upper yield is basically we're putting the stress in, the material's trying to hold together, so stress is going up and it's not moving anywhere, and then it lets go and the grain moves, and then it charges back up, and then the grain moves, so it drops down, and so on. So we're getting that pattern, and that's our upper and lower, charging the stress, releasing the stress, charging the stress, releasing the stress. Okay. Most of the time we only just think about the average point of that, which is a yield, but that's why what it is when it bounces around. Okay, and like I said, this now we've got, because we understand the yield point of this material, we understand where our safe working level or our safe working load is going to be for the given material we're using. So something like S355, so structural steel with 355 newtons a millimetre squared yield, means that if we apply a 2/3 working limit, so we come back down to what, like 200 and something, 280 or whatever 2/3 works out as being, if as long as we stay under that 200 and whatever newtons, then we won't ever hit the plastic level of our material, and that's good engineering bias, right? So at this point, no, our material is pretty much wrecked. We're not going to use it anymore. But if we continue to pull it and keep that force going on, we'll eventually reach what we call a UTS, so our ultimate tensile strength. And that is by pulling the material up and up and up. We can see our graph heads up, reaches a maximum, and then starts to fall. And at the point we meet the top of that crest, this is our UTS value. Okay, so it's got longer, and we have a UTS value here. Now, another word or another way of saying UTS is RM, so resistance maximum. So the maximum amount of stress that material will ever take, full stop. Okay, and immediately after that point, we start to see necking of the part. So the material's completely given up at this point, and it's pulling in material from the outside to allow it to continue to grow in length. Now, necking occurs immediately before failure, so that area from UTS to failure point, which we're going to see here, so we get a crack propagation occurring, and then that builds out and we have a failure point there. So the area before failure is our necking between the UTS and that point there. Okay, good multi-choice question coming up there. When does necking occur? It's immediately before failure or after the UTS point. Okay, so at this point the material's done, it's cracked in half, and we're pretty much done there. That's our test, and that's a very typical, well proportioned sort of a tensile test result where we get to see all of our individual points. Now, when we start talking about a fracture face and what it looks like, this is the point at which we can see that. So what we want to do now is look at the face of our tensile sample. So here's a picture I pulled off the internet, and what we can see is where the crack is, it starts to neck, so it's got that thinning of the material. But the face itself is what we refer to as rough and fibrous or rough and torn. It doesn't, it's broken, it's bitty, it's been pulled apart like that chewing gum or fairly ductile bit of material as you pull it away from each other. Okay, it exhibits everything we want to see within a ductile failure. Now, one of the big things here is what we refer to as shear lips at 45 degrees. So if you look at, let me just bring up my pen here. So if we look in this area here, this is our shear lip. So this is a pulling apart at 45 degrees. Now, in some cases, This can be a cup and ball type arrangement where one side gets the shear lips and the other side is more like a ball, and they fit back together and inside of each other. Okay, sometimes both sides have the shear lips as they pull apart and are cupped both equally, you know. But shear lips is the big thing. A rough in tone or rough and fibrous appearance with necking is what's going to constitute our ductile failure. And it's, you know, one of the things, if something fails, you look at it and you go, ductile failure, great. That means the material's held on for as long as it possibly could, and we have had no extra failure reason within that at our given test temperature. Great. Now, our next one, we're going to talk about brittle failure. So brittle failure is at the point at where we make materials cold, and what happens is the molecules, the grains within the steel are no longer vibrating with a very much power, so they slow right down. And like it says here, that gives rise to a harder material as such, right? What really happens is actually the yield point goes up as materials get colder, right? So it's going to take more energy, but the way it behaves when it fails tends to be a splitting, a cracking along grain boundaries or directly through the grains in an instantaneous failure. Well, when we say instantaneous, we mean at the speed of sound in that material. So, you know, fast enough not to really care. It's fast, okay? It's for us, it's pretty much straight away, okay? So brittle failure is always at a low temperature. So if you're looking at any multi-choice questions or anything like that, and it's referring to low temperature, 99% of the time, it's going to be talking about brittle failure within the structure. Okay. Now, most common test for detecting the susceptibility to brittle failure is a Sharpie V-notch or an impact test. Okay, very common test, which we talk about in other videos. So please go and give them a watch. Okay. Now, as a general question, then, what film best shows brittle failures? I'll give you 5 seconds. So 5, 4, 3, 2, 1. If you said the Titanic, get out of my lesson, go away, right? We don't want to hear. The best one that shows this is Terminator 2.
Baby.
Yeah. So if anybody remembers that scene, what happens is the liquid metal Terminator is somehow they're fighting in a steel mill, and there happens to be liquid nitrogen tanker coming along, which gets it crashes off the road, spills a load of the liquid nitrogen, comes into contact with the liquid Terminator, and that freezes them down and cools them down. So imagine, just like a Sharpie impact test, we're going to use liquid nitrogen, cool the sample right the way down, and then we're going to apply a force, an impact force. Now, Arnold Schwarzenegger uses a bullet to do that, but in our metallic test, we're going to use a pendulum and a hammer striker to hit the sample to detect how much energy is absorbed in making the part explode. Okay, so if you think about that, that is brittle failure and brittle failure testing in a nutshell, really. Okay. Now, for a brittle failure to occur, we need 3 things. So we need a flow, we need it to be at low temperature, and we need a material that is susceptible to this type of failure. Okay? Now, if you're looking at those 3 areas, what is a flow? Okay, now we could look at a flow being a welding defect or a material defect. It could be weld geometry, you know, the toe of a weld. a bit of slag inclusion, or maybe a non-metallic inclusion within the base material. There's lots of anything that's going to give rise to a stress concentrator within our structure is our flow. Right? Our low temperature, well, that could be something like the service life. So you're using cryogenic, you're carrying cryogenic materials within pipe work or a pressure vessel or something like that. Maybe it's just the ambient temperature. I don't know, somewhere like the North Pole, South Pole, somewhere like that, gets cold, drops the temperature of materials down. It could be non-expected. Okay, there could be a reason where your system was never designed to be cold and now it is cold. I don't know, ships, shipping container vessels being used in the wrong sea state, stuff like that. Okay. Now, a susceptible material we could characterize as things which aren't designed to be used at low temperature. So not all materials have been designed to be used under 0 degrees, but you can see these which are, so we said S355 before for our ductile. So if you have like an S355 J2 is tested down to -20 and so on. So we've got evidence. Now, let's say you've just gone lower than that acceptance level, then of course then you've got a susceptible material, something that hasn't been tested. Now, carbon steels generally are -60-ish. Okay, there's some outliers to that, but in the majority of the time, -60 we're starting to get into the realms of needing to change material out to something like a stainless steel or an aluminium, okay, which don't show this type of transition. Okay. Now, the way we test for this is we have a CVN chart, which we got here on the board. Here we're going to start with a carbon manganese steel, okay, because they show good transition temperature curves. So what we're going to do is we're going to take our material and we're going to machine the parts into our test sample, which is normally 10 by 10 by 55 millimeters long. Put a notch in it in line with the spec that we're testing, gives you the angle for the notch, the radius at the bottom of the notch, and all that type of thing. We then take test samples at different temperatures and we mark them onto our chart. Okay. And what you can see here is going from a positive number on the right to the minus numbers on the left. We can see the absorption energy gets lower as we drop the temperature because the material becomes more brittle, so it absorbs less energy in order to crack. Okay, we draw a line through all that to join all points, and this is what we call our transition curve. Okay, and what we're going to do is we're going to decide a test temperature against a absorption level that we want to have of energy. So I don't know, let's say it's 27 joules. Anything less than 27 joules is a failure. So where my question mark is here, I have 27 joules, I draw it across and I come back, our test temperature there is 27 joules is something like -15. Okay, so we can do this for all materials and all given acceptance criteria to decide what we want to do. Okay. Now, when we are above that line, we're going to say we're ductile, and when we're below our 27 joules, we're going to say we're brittle. So here's our transition temperature and curve that details that for our given material. Okay, and we do this for all the given materials. We then weld our test samples or weld qualification samples or PQRs and rerun the tests and compare them directly against the base material to make sure we're still maintaining that as a minimum. Okay. Now, these fracture surfaces, when they do break, are flat. So imagine something like glass when it breaks at very straight edges, very straight lines, very, very quickly. Okay. Now, so the way we describe that is flat and featureless. Now, the number you've got here is flat and shiny. You might see flat and crystalline. So when you hold it up in the light and you move it around, it sparkles a bit like crystals. Okay. But generally no deformation. Okay. It's flat, it has no shear lips, it has no tearing, it's never rough, it's always flat. Keep that in mind, right? In some cases, and it's very helpful for us, we have what we call chevron markings or chevron patterns. And these are chevrons which are showing the progression of the crack in the direction it came from and is heading to. So again, if we have a look back, and I'll grab my my pen here, what we've got in this, I don't know if anyone can see, sort of the chevron marks which are moving through this material in this direction. Okay, that means my crack is moving in that direction through this material. It's breaking and growing out. Okay, it's very helpful when we want to find areas of little locations where the crack initiated. So when we're looking for the defect that caused the failure, we can follow all these back to that one single point. Okay, so flat and featureless, crystalline appearance, sometimes with chevrons. Okay. Okay, so our final mode of failure is going to be fatigue. Now, our fatigue failures account for between 80 to 90% of all engineering failures. Ductile and brittle, we were able to design them out in some way. Ductile, we make our material strong enough. Brittle, we keep it warm. We never let it get to cold temperature. And we're kind of good, we're safe. However, with fatigue failures, our parts will fail through fatigue at some point in their life. Okay, what we want to do is get rid of any feature that will increase the likelihood of early failure. Okay, now as soon as we put a weld into something, we kind of screw this all up and we really affect fatigue lives. But we can look at that and try to understand how we use things like SN curves to understand how this works. Okay, so fatigue failures, what happens is, right, I start with a stress concentration, right, I apply that stress concentration to cyclic loading, so pressure on, pressure off, pressure on, pressure off, sometimes shown as sine waves and all sorts of things like that, right? What happens is that pressure on, pressure out starts to connect up at a micro level, and I start to produce micro cracks within my steel. Now, from the surface of the steel, what we get is a crack that heads off at about 45 degrees to the surface of the material for a very small amount. Okay, so that's my initial micro crack. Right? This is something that will happen everywhere, but of course is brought on more by if you've already got, say, micro cracks already existent in the surface of the steel, maybe a high stress concentration, like I said, like a toe of the weld or something like that, a crack from your welding process or something like that. But even in material which is inherently what we would say perfect, eventually these micro cracks through stages 1, 2, 3, 4 will appear, and this will happen. Okay, so that's our first stage, producing that little 45 degree crack. Our next stage is crack growth from this micro crack. Okay, so what then happens is our crack will start to head out at 90 degrees to the direction of stress. So you can see it changes direction and heads along, and then continues like that. More often than not, the crack in a fatigue crack is always 90 degrees to the direction of stress. Okay, that then grows out and gets longer and longer and longer until one of two things will happen. Either it eats its way all the way through the material thickness, and we reduce the remaining material so much that it fails through a secondary failure of ductile, because there's not enough material there to hold the weight of the structure. Or in some cases where we've got a cold environment, we might then trigger brittle. but in my experience, most of the time it goes fatigue to ductile. Okay. Right. And we can use things like Paris law to understand the rate of crack growth. Now, for weld inspection terms, we don't need to go into these calculations at any level. Okay, you won't. I just wanted to add it in to show you we can work this out, and we can sort of try to understand how the speed at which cracks grow through fracture mechanics of materials and things like that. If you want to see more videos on that, like and see you want to see them below in the comments, yeah, then I'll make one. So our final stage of failure is where we can look at materials cracked all the way through, and we can look at the fracture face. Now this is a very typical good example of a fatigue failure. So what we have is our initiation point in the middle of the curves. We have our beach marks as the crack has progressed through the material. This is all bound by a curve, and then outside of that curve we'll have a secondary failure, whether that be ductile or brittle, more commonly ductile. Okay, but you can see already the sort of the key words that snap out when we talk about failure faces here: beach marks, bounded by a curve, smooth, because that where we're inside of the curve is smooth as glass, really, because it's the fracture face of the crack. Okay, really easy to identify. If you're asked to draw any of these out, nice and easy to draw. Where I always find that crystalline and ductile failures are relatively difficult to do, but this failure is going to happen if we have a point of initiation. We always have a point of initiation, just some take longer to grow to a micro crack than others. Okay. Right, so there is our three. You can pause the video here if you want to read through this, but of sort of 3 stages of the crack. So we've got initiation, stage 1 of crack growth, stage 2 of crack growth. So stage 1 is your micro crack, stage 2 is it then grown out at 90 degrees to the structure, and then they finally break. Okay, but remember, in those beach marks being a really good sign that it is a fatigue failure. Now, one of the things we need to do when we talk about fatigue failures is try to work out the service life of a part. Now, we do that through what we call SN curves, so stress against the number of cycles to failure curve. Okay, this helps us understand the risk, and you will see different standards which actually give you welded structure output as well. Again, if you want to see that in more detail, I'm happy to make it. Put a like and comment below. But this is in just base material SN curve to get us started. Okay, so what we do is we take a specimen of material and we carry out fatigue tests at different stress ranges. So the first one on the left there, you can see we put a high amount of stress into it, and we've been cycling it on and off. So on, off, on, off, on, off at high stress. And the number of cycles is relatively low. Okay, and then you can see as the stress drops, the amount of cycles goes up, so it goes further to the right. And sometimes we have outliers, things don't always follow a perfect curve, and they sit around for a lot of different reasons. Homogeny of material and all sorts of things can kind of kick that out a bit. But what we do is we take all of our tests and then we draw a line through them, and that is now our curve. Okay, so from that, what we can do is work out an endurance limit. So you can see at the far right there, the lines start to become pretty much flat. And what we're going to assume here is anything below that stress range has not unlimited life, because it will eventually fail, but it's well outside of our service level and what we need to worry about as much as we can, But But what we can do is we can take our chart and we can take our stress range from what's in our engineering calcs and then work out how long that component is going to last in that stress range. So if I was to take 100 megapascals, okay, let's say that then kicks out at 500,000 cycles. Yeah. What I want to then do is say, well, if one cycle is per minute, so we go on and off every minute at my initial 100 MPa stress, time to failure would be about a year. Okay, so what we're doing here is being able to say, well, for our design, do we have to then change the stress level? Okay, or do I have a minimum amount of time it needs to last? How much stress can I put into it in reverse to that? Okay, so really handy. Now, in most cases, we have already existing standards that allow us to access them and use their SN curves to work on. DNV have one, C203, and you can go through and put your data in and get your expected life. But by maintaining quality of welds, this is what we're helping to improve is the fatigue life of our samples. Okay. Now, the stress SN curves I've just shown you are basically working on one very simple loading, 100 megapascals on, 100 megapascals off, and so on, backwards and forwards. But fatigue loading is never that simple. If you think of something like a bridge, you've got maybe a bus goes over it, then a car, then a person, then 6 buses and 5 cars. So the stress ranges are all different. Now there's different ways of calculating that. Again, we're not going to go into them today because it's a big subject by itself, and for inspection we don't need to know it at any real level. But so you've got some of these words in your head if you ever hear them. The way we account it for complex loading situations is something called rainfall counting. So we take the original stress history you can see here. We extract peaks and troughs and valleys from that, and we rain count it. And basically what we're doing is we're simplifying all of these ups and downs into blocks of how many times does the system see a high level, how many times does it see a medium level, how many times does it see a low level, and therefore we can understand at how many cycles and life we'll have at all of these combinations of inputs. We then use something called the minor rule, which calculates the amount of damage based off this information. Okay, if you're doing something like your engineering diploma or something like that, you will come across this within the design and calculation modules. Okay? But that is pretty much it. It's a whistle-stop tour of our 3 mechanical failures or our failure modes, okay, being ductile, brittle and fatigue. Hopefully from this you can see that ductile is just about making it strong enough. Brittle failure, keep it warm, never let it get cold, reduce the amount of flows you have for them stress concentrations to build up into cracks. Fatigue, it's always going to fail. No matter what, given enough time, given enough cycles, we will have the failure. But if we can understand the stress levels we're going to put into our parts, we can apply the standards and work out how long our component is actually going to last.